Good morning and welcome to today's session. Today we are going to discuss temporal difference learning, one of the learning method in reinforcement learning approach. In the last class we have discussed the Monte Carlo control. Now we will discuss the concept of temporal difference learning and also some backup diagrams to represent temporal difference learning. Next session we will address optimality of temporal difference learning. This TD0 is a special type of temporal difference that is called a one-step temporal difference. That is the theme of next session. Today we will see a basic introduction to the concept of temporal difference and its uses in reinforcement learning. Then we try to compare our dynamic programming approach in MTP and Monte Carlo approach that we are previously discussed. Then we will see the term temporal difference target, temporal error and related terms and its mathematical expressions. And finally we will see what is the advantages of temporal difference over Monte Carlo. First of all, let us see what is temporal difference and its use in reinforcement learning. The temporal difference method in reinforcement learning is a combination of best parts of MC and DP learning methods. That means it is a best choice from MC and DP. We take good part of MC and good part of DP for reinforcement learning. Okay. The name TD derives from its use of changes. That means the name temporal difference derives from its use of changes or difference in predictions over successive time steps to drive the learning process. We take a temporal difference. In this context, I would like to specify one term, spatial temporal. The spatial temporal is a common word associated with machine learning models and also in theoretical models related to engineering. What is a spatial temporal model? A model which make use of the spatial idea and also the temporal idea. Spatial means that is something related to the positions in coordinate system. In some coordinate systems, it may be Euclidean geometry, sometimes it may be non-Euclidean geometry. Anyway, in some coordinate system. Second point is temporal model. A temporal model is nothing but a model which make use of the time difference or the time component. It will make use of the changes in time. If it will start at time t0, then it will end at time tn, then that model behavior is fully controlled by the time variable t that varies from 0 to n. Many model which contains both spatial and temporal components, space and time components. But here I am using temporal difference. That means we consider the time difference effect. The time difference effect in updation rules. Okay, we will see more it in our mathematical derivation. Now we just observe how this dynamic programming, Monte Carlo approach and temporal difference approach unifies our learning theory. There are something common, but definitely there is something different. We try to address the difference and also try to find the common thing. Mathematically, the intersection part. Like Monte Carlo methods, TD methods can learn directly from raw experience without a model of the environment's dynamics. As you know, in Monte Carlo method, we calculate state values as averages of returns. We simply take samples of returns using episode idea, then Q value can be updated as averages of returns of various states in the episode. In that case, we are not using any environmental dynamics. Environmental dynamics means the probability distribution the TPM, the transition probability matrix that shows what is the probability for choosing an action from a state st to st plus 1, and also the reward dynamics. We are not make use of any previous experience. We just visit a state and we experience the movement or flow or action. Then based on that experience we calculate the return. We start from the initial position and go to the end and using some action. From that we got an approximate reward. We use this reward to update state values. That is the idea of MC. There is no probability approach. We directly use the sampling theory or sampling approach. We sample the rewards corresponding to a state and accept the state value as the average of this sampled return. That's all. TD make use of the same thing. TD methods can learn directly without considering any dynamics, the state or environment dynamics. The second thing, like DP, we just compare TD with DP. Like DP, TD methods update estimates based in part on other learned estimates without waiting for a final outcome. That is the idea of bootstrapping. Now TD is like DP. In what aspects? Always the DP make use of the next state values to update value of a particular state. That means I am in state ST. In order to update my state value ST, I will make use of the state value in the next state, that is ST plus 1. Okay. Here TD also make use of this idea. The ST value, the state value ST will be updated with the help of next state value without waiting to get the end return. So it has the characteristics of DP also. Okay. The difference is in the method. The difference in the method are primarily difference in their approaches to the prediction problem. So this temporal difference model skews out best from MC, Monte Carlo, and the dynamic programming, but the difference is lying in their approach in prediction problem. In a prediction method, in prediction situation, it will not make use of pure MC or pure DP. That is the difference. In working rule, it make use of good parts of both MC and DP, both Monte Carlo and dynamic programming. See, this is the easiest way to compare these three learning approach. One is Monte Carlo, that is leftmost, and center one is temporal difference, and rightmost is dynamic programming. We can consider Monte Carlo is the father, dynamic programming is mother, and temporal difference is a child. Now, for a first and best understanding, I will give you a mathematical analogy. See, you just only focused on this graph, this red shaded graph. Here also a small portion, here also we have a hilly structure portion. Now take intersection of this Monte Carlo red shaded region with dynamic programming red shaded region. Take the intersection, the common part. The common part is just, we start with this ST, ST is there, ST is here. So we put ST, then shading start from ST and go to this action. It goes to reward RT plus 1 and come to state ST plus 1. This part is common here. Same thing is here. So intersection of Monte Carlo and dynamic programming leads to temporal difference in its backup diagram. So backup diagram of a model gives its structure. So structurally temporal difference is intersection of both these two. Okay, now we can compare this. We revise Monte Carlo. We start from S1 and end at the terminal state. I choose a path. This is an episode. In that episode, I first calculate this terminal state ST state value. It is 0 here. Then I take the state value of next previous state, and using that I calculate all the state values. Okay, so I got return GT. Start from this terminal state. I got GT for this state, and first state. How we can calculate this reward. This reward can be calculated as sum of returns. That's all. Sorry, return can be calculated as sum of rewards. Now another point is that depending on various episodes, we have different returns to various states. Corresponding to a particular episode, I got a particular reward. Next episode, I got another reward. So we have a list of rewards. Sum of this reward is actually state value. That is the idea of Monte Carlo. Now we can write a general update formula for Monte Carlo like this. V of st, value of st, can be updated by value of st now plus alpha into return at state st minus value of st. This actual return at st minus value of st is called an error. So this is called a constant alpha Monte Carlo updation rule. That means this V of st will be updated, make use of the current value of st and this difference. Okay, what happened when alpha is equal to 0? This alpha is usually lies between 0 and 1. When alpha is equal to 0, the state value V of st will be same as state value V of st. That means there is no change in this iteration. That means it is consistent and so it is converges. If alpha is less than 1, when alpha is less than 1, what happened? This alpha has some rule here. When alpha is equal to 1, both this term has a rule. When alpha is equal to 0, this update part or the error part has no rule. So alpha into gt minus v of st become 0 when alpha equal to 0. When alpha is equal to 1, both this term v of st, the current value of state st, and also this difference is actually the difference between the state value v of st and the return at states st. Okay, then compare this formula with the new formula. This is the formula for temporal difference. This is for constant alpha Monte Carlo update rule. This is temporal difference update rule. V of st, here also V of st, is updated by V of st plus alpha into, instead of gt, I am using rt plus 1 plus gamma into V of st plus 1. See, rt plus 1 is the immediate reward or immediate return to state st for an action. Then gamma is our discount rate. V of st plus 1 is the value at next state. So this value is the return based on next state value. This gt is return based on the complete traversal from the starting state st to the end state t. But here rt plus 1 plus gamma into V of st plus 1 is just return based on next state value. So this gt is depending on the entire transversal, but this rt plus 1 plus gamma into V of st plus 1 just depend on one step transition. See, one step transition. This needs the entire transition, entire traversal along this path. Okay, so gt is replaced by this one step transition. Again, it is depending on V of st plus 1. So in Monte Carlo method, it is never based on nearest state values. Each state value is independent of the nearest state values or any other state values. That is the idea of Monte Carlo. But here it is not like that. The value of state st is depending on value of state st plus 1. Now this difference is called temporal difference. That means we update V of st using the temporal difference. Why we call it as temporal difference? It is simply a one step difference of return. This is the return from st plus 1. This is the actual or our assumed return at st, assumed value at st. So this temporal difference is used to update the state value of V of st. This is not temporal difference. Here we use the complete transversal to calculate gt. That is the difference. Now let us compare temporal difference with dynamic programming. That is for Markov decision process. See, a V of st is calculated a expectation of the same thing, rt plus 1 plus gamma into V of st plus 1. In this case, remember, we have to take expectation of what? All immediate return. So it has to move from ST and to reach all other states which is connected to ST and take this immediate reward and calculate this expectation. That is the idea. Then how we will calculate expectation? It is not a simple average. We make use of the environment dynamics, the probability distribution, the transition probability matrix to calculate everything. We are familiar with this dynamic programming approach in MDP. Okay, so it needs the full values of these states, ST plus 1, ST plus 2, etc., everything that connected to this ST. But each ST plus 1, ST plus 2, etc., connected to another state values, and so this sweeping continues and it goes over and over again. That is why dynamic programming make use of our bootstrapping concept. Now for simplicity, you just think like that this temporal difference is intersection of Monte Carlo and dynamic programming in concept. Okay, now we will form mathematical expressions for TD prediction using an update formula. Both TD and Monte Carlo methods use real samples. That means experience. We have the experience with Monte Carlo. In Monte Carlo, we just start the game, we start the trial, then visit all the states, then we assess the rewards corresponding to each state. That is from experience. When we get the experience, when we sample a particular environment, or we take values from a particular environment, we will get an experience. So from real samples we form the state values for Monte Carlo. We use almost same approach for TD also. We just visit next state, then using the next state value I update my existing state value. Okay, so V of ST changes to V of ST plus, or updated to V of ST plus some learning rate alpha into GT minus V of ST. This is our alpha, constant alpha MC value update. Now this GT is updated with immediate return, that is called a TD update, temporal difference update. Why it is called a temporal difference update? This update or this return is obtained by moving from state ST to ST plus 1, ST to ST plus 1, or it is also known as TD target, RT plus 1 plus gamma into V of ST plus 1. Then this difference TD update minus current state value is called the error or temporal error. It is denoted by delta. So delta T, temporal error at state ST, is equal to RT plus 1 plus gamma into V of ST plus 1 minus V of ST. Okay, we are using this formula for temporal difference update. This is called temporal difference update. Instead of this expression in bracket, I can denote delta T also. See, this expression has some similarity with our greatest descent and greatest ascent methods in stochastic approaches. For example, stochastic gradient, gradient ascent and gradient descent in our machine learning algorithms. It is a learning process. This is called the temporal difference learning. V of ST is updated with this rule. This updation is called a learning process. Okay, then this temporal difference method is called TD0. Why it is called TD0? Here I use only one step transition. If I use more steps in this transition, it will become TD lambda. That is another idea. That is an extension of TD0 with some more theoretical background. Now let us see a pseudo code for TD0 prediction. We calculate TD0 at a state ST. There are many states in a particular model, so we have to update every state using this TD rule. So we have to iterate over all states. Since it make use of the Markov chain idea, we will use different episodes, and based on these episodes we decide what is the state value of the state Vt plus 1. Using that Vt plus 1, we update the current state. So the tabular TD0, the TD0 is generally known as tabular TD0 when we try to update each state value consecutively. Input is a policy. We have to visit the state according to this policy. Algorithm parameter, that is an alpha is lies between 0 1. When this alpha is equal to 0, there is no learning happened. When alpha is equal to 0, what happened? V of S is equal to V of S itself. It will stand still. So we specify alpha is element of open 0 closed 1. Initialize v of s. We start with an initial value. Usually we choose v of s equal to 0 for all states, or we can choose random numbers, that is our choice. Then it is for all s element of s plus. S plus means state space containing the terminal states also. In our approach, we assume that the terminal state has the value 0. So v of s equal to 0 for all states, okay. Then arbitrarily accept that v of terminal equal to 0. See, in this algorithm we specify then end terminal is must be state value 0. If v of s equal to 0 for all s, then automatically this condition will satisfied. Okay. Then loop over all each episode. We have to consider many episodes to get good result. For each episode, that means a movement from starting state to our end state, initialize s. We have to initialize the state s. That means we just fix a state s. Loop for each step of the episode. We start from s1, s2, etc. end state. Then we fix an action that leads from state st to next state. For simplicity, I use the starting fixed state is s. So I start an action from s to next state s dash. This action should be governed by this policy pi. Then take this action, observe r and s dash. That means observe the return for this action and the state to which that action leads. V of s equal to our temporal difference update v of s plus alpha into r plus gamma into v of s dash minus v of s. Then we update s by s dash. That means we change our position. Now we are at s and calculate temporal difference update for the state s, and this value is updated like this. Next I move on to next state, that is s dash. Then we continue this till the terminal state is reached, that is one episode. Then we start with next episode. After this after a long number of iterations, we got a consistent value for the state s v of s. At that state we will stop this algorithm. So this is the temporal difference update in TD0 approach. Then TD process qualities of both MC and DP. That means the temporal difference model possesses both the good qualities of MC and DP mathematically. In previous slide I show it with the help of backup diagram. Now I will show it with a mathematical definition. See, v pi of st, value of a state st, can be defined as dot equal to means defined as expectation under the given policy gt, the return at state s. I stand on a state s, then I calculate the expected value of return, that is called the v pi of st. This is the basic definition. If this gt, the return, is calculated using sampling, this formula gives Monte Carlo. If gt is calculated using sampling, that from the starting state s1 to end state t, then calculate different rewards, then calculate returns for each state as return plus immediate reward. Then we take the average. This expectation is simple average. Then that value is actually Monte Carlo estimate. When this gt can be written as rt plus 1 plus gamma into gt plus 1. This gt means immediate reward at state t plus reward to the next state. Then I am using my discount factor gamma. If gamma is equal to 1, the reward is not, or the return is not discounted. We take the return at the next state as itself in the current state. There is no depreciation in return under the state st is equal to s. Now in this formula, the current state value is depending on immediate reward plus next stage value. If gt plus 1 is written in the form of v of st plus 1, see, gt plus 1 is the reward for next state, the return for next state. If this gt plus 1 is the value of st plus 1, this gt plus 1 can be calculated as either sampling average or expectation using our dynamic programming approach. If it is calculated using our MC approach, this is again a Monte Carlo formula. Now RT plus 1 plus gamma into V of ST plus 1, if it is value of the next state, then this formula is called the temporal difference formula. Why? This current state value is calculated in terms of return plus next state value. This is our temporal difference formula. So how we calculate GT, that is very important. If we calculate this GT plus 1 as sample average, then it becomes a Monte Carlo approach. If the same GT plus 1 is calculated as value of ST plus 1 using the dynamics, then it is called the DP algorithm. So V pi of ST can be calculated either using Monte Carlo sampling approach or the approach by DP. If that approach is by DP, then it becomes a best temporal difference. Both these leads to temporal difference. If we use the Monte Carlo approach, it will become a good approach. TD is similar to that of DP. So TD possesses characteristics of both MC and DP. That's all. Or TD has all the good characteristics of MC and DP in its structure. Okay. Now one more note, that is about expectation and unbiasedness. A parameter theta is called unbiased if E of theta is equal to mu. E of theta is equal to mu, then this theta is called unbiased estimate of this mu. See, this is an expectation. You just look into this definition and avoid this state reference ST is equal to S. So V pi of ST is equal to expectation under pi RT plus 1 plus gamma into V of ST plus 1. That means this is my theta, this is my mu. Expectation of theta is equal to mu. Expectation of theta is equal to mu. That means this theta RT plus 1 plus gamma into V of ST plus n is an unbiased estimate of ST. That is why this temporal difference gives good results. I repeat, this temporal difference RT plus 1 plus gamma into V of ST plus 1, this is actually TD estimate or a TD update. This TD update is, it is our theta, that is an unbiased estimate of the state value ST. I repeat, the TD estimate or TD target is an unbiased estimate of current state value. That is why mathematically this temporal difference model gives better result. Okay. Now bucket diagram for TD0. This I start with state ST and I choose an action, then moves on next state. Using this state value, I update current state value. See, here the state is important. Current state, next state. The next state value is calculated either using the state dynamics or using our sampling approach. Anyway, we need this state value. Using this state value, I calculate my current state value. This is TD0. Now temporal error and relationship between successive errors. See, delta T is actually our temporal difference. It is denoted by GT minus V of ST. The return at state T minus value of state ST, that is called a temporal error delta T. Now this GT in temporal difference model, GT is nothing but RT plus 1 plus gamma into GT plus 1. Immediate return or reward plus next state value. Now I just add and subtract this term gamma into V of ST plus 1 minus gamma into V of ST plus 1. That is a mathematical manipulation. So this expression remains as the same. Then I add gamma into V of ST plus 1 and subtract gamma into V of ST plus 1. When I simplify this expression, I got back this. Then I take RT plus 1 plus gamma into V of ST plus 1. RT plus 1 plus gamma into V of ST plus 1 together minus V of ST. RT plus 1 plus gamma into V of ST plus 1 minus V of ST plus 1 is nothing but delta of T. Immediate reward plus gamma into next state value minus current state value. That is our temporal error delta T. The remaining term gamma GT plus 1 minus gamma VST plus 1. Now what is common in these two terms? We can get a gamma from here and also from here. So I get gamma outside. So delta T plus gamma into GT plus 1 minus V of ST plus 1. Now look back, I am starting from gt minus v of st, then I reach delta t plus gamma of gt plus 1 minus v of st plus 1. Okay, so gt minus v of st can be replaced by gamma t plus delta t plus gamma into gt plus 1 minus v of st plus 1. I am using this expression recursively here. So delta t plus gamma into, instead of this delta t I choose delta t plus 1. Delta t plus 1 plus gamma into gt plus 2 minus v of st plus 2. Then multiply this expression with the common factor gamma. So gamma into delta of t plus 1 plus gamma into gamma square. Again I substitute gt plus 2 minus v of st plus 2 in terms of this expression, that is delta t plus 2 plus gamma into gt plus 3 minus v of st plus 3. Again we can multiply this entire expression with this gamma square. So gamma square into delta t plus 2 plus again gamma cube into this expression. I can resubstitute it. When I continue like this, I got an expression in terms of powers of gamma. So gamma raised to 0, that is 1 into delta t plus gamma raised to 1 delta t plus 1 plus gamma square delta t plus 2 plus etc. gamma raised to t minus t. At last what happened? The state t values increased and up to reached t. So gt minus v of st. V of st, the end terminal value is 0, and so definitely the return from end state value is 0. So 0 minus 0, gt minus v of st 0. So the last time gamma raised to capital T minus t becomes 0. So the remaining expression is a power series in gamma. I can write in sigma expression. Sigma, here this is gamma raised to 0. So I can choose a variable k from 0 to end time. So k is equal to tt to t minus 1. K is equal to t to t minus 1. Gamma raised to k minus t into delta k. When I put k is equal to t, I got delta t gamma raised to 0. So delta t gamma raised to 0 is 1. Then when I take k is equal to t plus 1, gamma t plus 1, not gamma t plus 1, delta t plus 1 into gamma raised to t plus 1 minus t. So gamma raised to 1. So gamma. So we got delta t. That means the temporal error at state t is equal to sum of discounted temporal errors, at various states. See, temporal error is equal to sum of discounted temporal errors at various states. So there is a possibility to extend one step temporal difference into n step temporal difference. So this is the relationship between the current state temporal error and the next immediate and next immediate, and in that fashion to the end state temporal errors. So we can calculate current state temporal error in terms of the next coming state temporal errors, delta k plus 1, delta t plus 1, delta t plus 2, delta t plus 3, etc. So that is a mathematical derivation for temporal difference at a particular stage in terms of temporal errors or temporal difference of consecutive states. Now we are going to explain a very simple formula for this temporal difference update. We have seen the current state value can be updated in terms of current state value and temporal or TD update or TD target. That is, V of S is replaced by or updated by the current value V of S plus alpha into, alpha is called learning rate, into immediate return or immediate reward plus gamma into value of the next state minus value of S. This is called the TD update or TD target, one step TD target, the target minus the current state value. Okay, now I make some adjustment. I just multiply this expression by alpha, this outside alpha. So V of S plus alpha into R plus alpha gamma V of S dash minus alpha into V of S. Then I make this V of S outside. So here V of S, along with this V of S I have coefficient 1. Here I have minus V of S, the coefficient is alpha. So alpha into minus is minus alpha. So coefficient of V of s in this expression is 1 minus alpha. 1 minus alpha into V of s plus then alpha into r plus this term, r plus gamma into V of s dash. R plus gamma into V of s dash is our temporal difference target in one step. So now look into this expression in terms of alpha. It is a combination of 1 minus alpha and alpha, or it is a convex linear combination of V of s and r plus gamma into V of s dash. Now in terms of algebra, V of s and r plus gamma into V of s dash are here important parameters. This 1 minus alpha is obtained from this alpha. So alpha is our learning rate. So V of s and r plus gamma into V of s dash are variables. So what is V of s? Current state value. Then r plus gamma into V of s dash is actually TD update or TD return in one step. Current state value, r plus gamma into V of s dash can be interpreted as I just give you a hint, expectation of theta is equal to mu. This is my theta. So r plus gamma into V of s dash is an unbiased estimate for V of s. R plus gamma into V of s dash is an unbiased estimate of V of s. Or in short, this capital V of s can be written as a convex linear combination of V of s and its unbiased estimate. V of s and its unbiased estimate. V of s and its estimate. That is the idea. Then what happened when alpha near to 1? When alpha is equal to 1, what happened? This becomes 1 minus 1, 0. That means there is no role for V of s. So it is completely predicted by the unbiased estimate of V of s. When alpha come near to 0, very close to 0, what happened? This update has no meaning. The TD update has no meaning. In that case, this 1 minus a very small quantity, that is come near to 1. So V of s near to V of s itself. In that case, this V of s converges to a particular value. That is the main idea. In simple linear algebra terms, the TD update formula is a convex linear combination of current state value and its unbiased estimate. This unbiased estimate is actually immediate return plus gamma, the discount factor, into current next state value. Okay. So this is an easy formula to relate the temporal difference update in terms of the current state value and temporal difference target. It's a convex linear combination. This is it's a very important idea in linear algebra. So we can deal this TD update formula in terms of linear algebraic update using convex linear combination of current state value and its unbiased estimate. Okay, thank you. Next slide we will see optimality of TD of 0. In that session we will discuss how this one step TD is optimized. It is more mathematical than code referral. Okay, thank you very much.